In the rapidly evolving landscape of energy storage technology, the shift from traditional lithium-ion batteries to solid-state batteries represents a pivotal advancement that could reshape the electric vehicle industry and beyond. As of early 2026, researchers, engineers, and industry leaders are increasingly focusing on solid-state batteries as a superior alternative to the lithium-ion batteries that have dominated the market for decades. These conventional lithium-ion batteries, which power everything from smartphones to electric vehicles, rely on a liquid electrolyte to facilitate the movement of lithium ions between the anode and cathode during charging and discharging cycles. This liquid medium, typically a mixture of organic solvents and lithium salts, allows for efficient ion transport but comes with inherent drawbacks that have long plagued the technology. Experts argue that while lithium-ion batteries have enabled the widespread adoption of portable electronics and electric mobility, their limitations in terms of energy storage capacity, safety risks, and operational efficiency are becoming increasingly apparent in an era demanding more sustainable and high-performance solutions. To understand the core advantages of solid-state batteries, it is essential first to delve into the mechanics of traditional lithium-ion batteries. In a standard lithium-ion battery, the anode is usually made of graphite, which stores lithium ions, while the cathode consists of metal oxides such as lithium cobalt oxide or lithium nickel manganese cobalt oxide. The liquid electrolyte serves as the conduit for lithium ions to shuttle back and forth, enabling the flow of electrons through an external circuit to generate electricity. This design has proven reliable and scalable, with current lithium-ion batteries achieving energy densities ranging from 160 to 250 watt-hours per kilogram. However, the reliance on a liquid electrolyte introduces several vulnerabilities. For instance, the liquid can degrade over time due to chemical reactions with the electrodes, leading to reduced battery capacity after repeated charge-discharge cycles. Moreover, under extreme conditions like high temperatures or physical damage, the flammable nature of the organic solvents can trigger thermal runaway, a chain reaction where the battery overheats, potentially leading to fires or explosions. This safety concern has been highlighted in numerous incidents involving electric vehicles and consumer devices, prompting recalls and regulatory scrutiny worldwide. One of the most pressing limitations of lithium-ion batteries is their limited range when applied to electric vehicles. With energy densities capped at around 250 watt-hours per kilogram in top-tier models, most electric vehicles today offer driving ranges of 300 to 500 miles on a single charge, depending on factors like vehicle weight, aerodynamics, and driving conditions. This range anxiety remains a significant barrier to broader adoption, as consumers often compare it unfavorably to the quick refueling times of gasoline-powered cars. Additionally, charging speeds are constrained by the liquid electrolyte's ability to handle high currents without overheating or forming dendrites, needle-like lithium deposits that can pierce the separator between anode and cathode, causing short circuits. Fast charging protocols can reduce charging times to 30 minutes for an 80% charge, but this often comes at the expense of battery longevity, as repeated fast charges accelerate degradation. Environmental factors exacerbate these issues. In cold weather, the viscosity of the liquid electrolyte increases, slowing ion movement and reducing effective capacity by up to 40% in sub-zero temperatures. These shortcomings have spurred billions of dollars in research investments aimed at overcoming them, with solid-state batteries emerging as the frontrunner for next-generation energy storage. Solid-state batteries fundamentally differ from their lithium-ion counterparts by replacing the liquid electrolyte with a solid material, such as ceramics, polymers, or sulfides. This solid electrolyte not only conducts lithium ions but does so in a more stable and efficient manner, unlocking a host of advantages that address the core pain points of traditional batteries. At the heart of this innovation is the potential for dramatically higher energy density. By using a solid electrolyte, battery designers can incorporate lithium metal anodes instead of graphite, which has a theoretical capacity 10 times greater. This allows solid-state batteries to achieve energy densities ranging from 250 to 800 watt-hours per kilogram, potentially doubling or even tripling the storage capacity in the same physical space or weight. For electric vehicles, this translates to ranges exceeding 1,000 miles on a single charge, effectively eliminating range anxiety and making long-distance travel feasible without frequent stops. Industry analysts project that widespread adoption of such batteries could accelerate the transition to electric mobility, reducing global dependence on fossil fuels and cutting transportation-related emissions by significant margins. Safety emerges as another cornerstone advantage of solid-state batteries. The absence of flammable liquids virtually eliminates the risk of thermal runaway, as solid electrolytes are non-volatile and do not leak or react explosively under stress. This enhanced thermal stability allows solid-state batteries to operate safely at higher temperatures, up to 150 degrees Celsius in some designs, without compromising performance. In contrast, lithium-ion batteries must incorporate complex cooling systems and safety mechanisms, adding weight and cost to electric vehicles. Experts from research institutions emphasize that this safety profile could revolutionize applications in aviation and heavy-duty transport, where battery failures pose catastrophic risks. For instance, short-haul electric aircraft and electric trucks could benefit from lighter, safer power sources that tolerate the rigors of operation better than current technologies. Furthermore, the solid structure reduces the likelihood of dendrite formation, which in lithium-ion batteries can lead to internal short circuits over time. This not only prevents failures, but also contributes to a more reliable energy storage system overall. Charging speed represents a game-changing benefit, with solid-state batteries capable of accepting charges up to 4 times faster than lithium-ion equivalents. The lower internal resistance of solid electrolytes, often 2 to 3 times less than liquid ones, enables ultra-fast charging without excessive heat buildup. Prototypes have demonstrated full charges in as little as 10 minutes, akin to refueling a gasoline vehicle, which could transform user convenience and infrastructure needs. Imagine electric vehicle owners pulling into a station for a quick top-up during a coffee break, rather than waiting hours at home or public chargers. This capability stems from the solid electrolyte's ability to handle higher current densities while maintaining structural integrity. In cold climates where lithium-ion batteries suffer from slowed ion kinetics, solid-state versions perform admirably, retaining up to 90% of their capacity even in freezing conditions. This resilience broadens the appeal of electric vehicles in diverse geographies, from Arctic regions to tropical zones, fostering global market penetration. Longevity and cycle life further underscore the superiority of solid-state batteries. Traditional lithium-ion batteries typically endure 1,000 to 2,000 charge-discharge cycles before capacity drops below 80%, necessitating replacement. Solid-state designs, however, degrade more slowly due to the chemical stability of their electrolytes, potentially lasting 5,000 cycles or more with minimal capacity loss. This extended lifespan translates to lower long-term costs for consumers, as batteries in electric vehicles could outlast the vehicle's operational life, reducing the need for expensive replacements. From an environmental perspective, fewer battery replacements mean less mining for raw materials like cobalt and nickel, which are associated with ethical and ecological concerns. Solid-state batteries often require fewer rare earth elements, easing supply chain pressures and geopolitical tensions over resource control. Researchers note that this durability also supports grid-scale energy storage, where batteries cycle frequently to balance renewable sources like solar and wind. In terms of size and weight, solid-state batteries offer compact and lightweight alternatives. Without the need for a porous separator to prevent short circuits, a staple in lithium-ion designs, the overall battery pack can be smaller. The use of lithium metal anodes, which are lighter than graphite, further reduces weight, potentially shedding hundreds of pounds from electric vehicles. This weight savings improves efficiency, extends range per charge, and minimizes wear on components like tires and suspensions. As electric vehicles grow larger to accommodate families and cargo, maintaining a lightweight profile becomes crucial to curb secondary pollution from tire particulates, a growing environmental issue. Solid-state batteries' higher volumetric energy density, up to 70% greater than lithium-ion, allows for more energy in less space, enabling sleeker vehicle designs without sacrificing performance. Environmental and sustainability benefits round out the advantages, positioning solid-state batteries as a greener option. Their production can have a lower carbon footprint, especially if scaled with renewable energy, and the absence of toxic liquids simplifies recycling processes. Unlike lithium-ion batteries, which require careful handling of hazardous electrolytes during disposal, solid-state versions are more benign. This aligns with global pushes for circular economies, where materials are reused rather than discarded. Moreover, by enabling more efficient electric vehicles, solid-state batteries could accelerate decarbonization efforts, supporting international climate goals. However, challenges like high initial manufacturing costs and scalability hurdles remain, but ongoing breakthroughs suggest these will be surmounted in the coming years. Experts across the board describe solid-state batteries as addressing the trifecta of limitations: limited range, slow charging, and safety concerns that have hindered widespread electric vehicle adoption. As one physicist noted in a recent analysis, the transition to solid electrolytes not only boosts energy density by 40% per weight, but also enhances overall system efficiency. This optimism is echoed in industry roadmaps, with major automakers investing heavily in solid-state research. While lithium-ion batteries laid the foundation for the electric revolution, solid-state technology promises to build upon it, ushering in an era of safer, longer-lasting, and more capable energy storage that could fundamentally change how we power our world. In the fast-paced world of electric vehicle innovation, recent months have brought a surge of announcements signaling that solid-state battery technology may finally be transitioning from prolonged research phases into tangible, real-world deployments. As of January 2026, several companies have captured significant attention with claims of breakthroughs that could accelerate the adoption of this long-promised technology. These developments, unveiled at major events and through corporate statements, highlight progress toward overcoming manufacturing hurdles and delivering on the superior performance that solid-state batteries promise over traditional lithium-ion designs. One of the most prominent stories emerged from the Consumer Electronics Show held in Las Vegas in early 2026, where an Estonian-Finnish startup called Donut Lab made headlines by unveiling what it describes as the world's first production-ready all-solid-state battery. The company positioned its Donut battery as a game-changer, already integrated into vehicles and available for original equipment manufacturer use. Donut Lab claims its solid-state cells achieve an energy density of approximately 400 watt-hours per kilogram, which represents nearly double the energy storage capacity found in many leading lithium-ion batteries currently on the market. This higher density allows for significantly more energy to be packed into the same volume or weight, potentially extending vehicle ranges dramatically while keeping battery packs compact and lightweight. Donut Lab further asserts that its batteries enable ultra-fast charging, with full charges possible in as little as 5 minutes under optimal conditions. This capability stems from the solid electrolyte's lower internal resistance and ability to handle high current flows without excessive heat generation or degradation. The batteries are also touted for exceptional durability, designed to withstand up to 100,000 charge-discharge cycles with minimal capacity loss, far surpassing the typical 1,000 to 2,000 cycles of conventional lithium-ion packs. Safety features stand out prominently in the company's messaging, with the non-flammable solid electrolyte eliminating risks associated with thermal runaway that have plagued some lithium-ion incidents. Additionally, the batteries reportedly maintain over 99% of their capacity even at temperatures as low as -30 degrees Celsius, addressing a major weakness in current electric vehicles that lose substantial range in cold weather due to slowed ion movement in liquid lights. To demonstrate real-world viability, Donut Lab partnered with Verge Motorcycles, an innovative electric motorcycle manufacturer known for its hubless wheel motors. The Verge TS Pro model, already in production since around 2022, has been upgraded with Donut Lab's all-solid-state battery packs. Available configurations include a 20.2 kWh pack or a larger 33.3 kWh version, delivering ranges of up to 217 miles for the standard pack and up to 370 miles, or approximately 600 kilometers, for the long-range variant on a single charge. The upgraded TS Pro boasts impressive performance metrics, including 737 pound-feet of torque, 0 to 60 miles per hour acceleration in 3.5 seconds, and seamless integration with the company's frictionless rim motor for high efficiency. Verge Motorcycles announced that all 2026 model year bikes, including the TS Pro and Ultra variants, would feature these solid-state batteries, with customer delivery scheduled to begin in the first quarter of 2026. Orders opened immediately following the announcement, marking what the companies call the first production vehicle equipped with true all-solid-state battery technology hitting the roads. Industry coverage of the CES 2026 reveal has been extensive, with outlets noting the motorcycle's poppy orange California edition display and hands-on demonstrations of the compact, smartphone-sized solid-state cells that feel remarkably light. Donut Lab emphasizes that its batteries use globally abundant materials, potentially reducing costs below those of lithium-ion equivalents and easing supply chain dependencies on rare elements like cobalt. The company claims gigawatt-hour level production capacity is already in place, with batteries manufactured in facilities in Estonia and Finland, positioning the technology for broader original equipment manufacturer adoption across transportation sectors. However, enthusiasm has been tempered by calls for independent third-party verification, as some observers question whether the extraordinary specifications, 5-minute full charges, extreme cold resilience, and massive cycle life had been fully substantiated in rigorous public testing beyond company-controlled demonstrations. Parallel to the Donut Lab Verge collaboration, Chinese automaker Chery has generated substantial buzz with its own solid-state battery ambitions. In mid-January 2026 announcements, Chery confirmed plans to integrate its Rhino S solid-state battery into the Exeed Lifeng, a premium shooting brake model under its Exeed luxury brand. The company targets deployment later in 2026, with the battery boasting an exceptional cell-level energy density of 600 watt-hours per kilogram, among the highest claims in the industry. This oxide-based solid electrolyte approach, combined with lithium-rich manganese cathodes and in-situ polymerization techniques, is designed to deliver outstanding performance in extreme conditions. Chery highlights the Lithing's projected range of 1,500 kilometers under the Chinese light-duty vehicle test cycle, even when operating in sub-zero temperatures as low as -30 degrees Celsius. This cold-weather prowess addresses a critical limitation for electric vehicles in regions with harsh winters, where conventional batteries can lose 40% or more of their effective capacity. The vehicle is expected to pair the battery with an 800-volt architecture for rapid charging, sub-3 seconds 0 to 60 mph acceleration, and a top speed around 162 mph. With a sleek one-box interstellar design and a low drag coefficient of 0.22, the Lifeng aims to validate the technology under real driving scenarios, starting with limited production runs to gather performance data before wider scaling. Chery's move positions it as a potential early leader in passenger car applications, potentially outpacing some established players in bringing solid-state batteries to market. Beyond these headline-grabbing initiatives, other major automakers continue steady advancement in solid-state battery development. Toyota maintains its long-term roadmap, with prototypes and road tests progressing towards small-batch integration, possibly by 2026 or 2027, followed by broader commercialization around 2027 to 2028. The company has emphasized improvements in durability and fast-charging capabilities, targeting ranges exceeding 600 miles with 10-minute charges in future iterations. Honda pursues independent solid-state efforts aiming for production vehicles in the second half of the decade, while Mercedes-Benz conducts ongoing road tests of prototypes incorporating semi-solid or full-solid state cells from partners like Factorial Energy, with demonstration fleets planned for 2026. These efforts reflect a collective industry push to resolve lingering challenges such as material stability, interface issues leading to cracking under stress, and economical scaling for high-volume automotive use. Overall, the flurry of announcements in early 2026, from Donut Labs' motorcycle deployments to Chery's passenger car plans and continued progress by legacy manufacturers, marks what many describe as a pivotal moment for solid-state batteries. While skepticism persists regarding unverified claims and historical delays in the field, the presence of vehicles reportedly entering customer hands or nearing launch provides rare opportunities for real-world validation. If these initial deployments prove reliable, they could catalyze accelerated investment, regulatory support, and infrastructure adaptations, bringing the full transformative potential of solid-state technology closer to mainstream electric mobility in the years ahead. In the competitive arena of solid-state battery development, numerous established automakers and their strategic partners continue to advance the technology through rigorous research, prototype testing, and planned integration timelines. As of January 2026, these efforts reflect a concerted push to resolve persistent technical obstacles, including material durability, interface stability, scalability of production, and cost reduction, while positioning solid-state batteries for broader automotive applications in the coming years. Toyota stands as one of the most prominent and long-standing players in solid-state battery research, having invested decades and billions into the field. The Japanese automaker has consistently outlined ambitious roadmaps, with recent updates confirming progress toward commercialization. Toyota's breakthrough in solid-state technology focuses on sulfide-based electrolytes, which promise exceptional ion conductivity and compatibility with high-energy lithium metal anodes. The company has overcome earlier durability challenges, such as shorter expected battery life under high voltage and temperature conditions, through material innovations that enhance longevity without sacrificing performance. Toyota aims for the first solid-state batteries to deliver at least a 20% increase in driving range compared to its high-performance liquid electrolyte packs, alongside ultra-fast charging times of 10 minutes or less from 10% to 80% state of charge. Higher specification versions under development could boost range by up to 50% over current benchmarks. Production plans certified by Japan's Ministry of Economy, Trade and Industry include starting limited manufacturing of advanced batteries, including all solid-state cells from 2026 onward with gradual ramp-up. Mass production is targeted for 2027 to 2028, initially for premium or high-performance models, potentially in hybrid electric vehicles before full battery electric vehicle integration. Partnerships with suppliers like Idemitsu Kosan for lithium sulfide production and Sumitomo Metal Mining for cathode materials support this timeline, ensuring a secure supply chain for key components. Toyota's approach emphasizes reliability and cost competitiveness, with prototypes undergoing extensive road testing to validate real-world performance across diverse climates and driving scenarios. Honda pursues a parallel but independent path in solid-state battery development, prioritizing in-house innovation to control costs and specifications from the outset. In late 2024, Honda unveiled a demonstration production line for all-solid-state batteries at its research and development facility in Sakura City, Tochigi Prefecture, Japan. This line replicates mass production processes and began test production in January 2025, allowing the company to verify manufacturing techniques, refine cell designs, and assess costs across every step. Honda's focus includes material specifications and scalable fabrication methods to address challenges like dendrite formation and electrolyte electrode interface degradation. The automaker plans to apply its all-solid-state batteries to electrified mobility products in the second half of the 2020s, targeting improvements in range, charging speed, safety, and overall affordability. By emphasizing proprietary technology, Honda aims to double electric range potential, reduce battery size by up to 50%, cut weight by around 35%, and lower costs by 25% compared to current generations. This roadmap aligns with broader electrification goals, positioning solid-state cells for integration into future passenger vehicles and other applications, with verification ongoing to ensure durability under real-world stresses. Mercedes-Benz continues aggressive real-world validation of solid-state technology through its collaboration with Factorial Energy, a Massachusetts-based innovator specializing in lithium metal cells using Factorial electrolyte system technology. In 2025, Mercedes-Benz conducted a landmark demonstration drive in a modified EQS sedan equipped with Factorial solid-state cells. The vehicle covered 1,205 kilometers, approximately 749 miles from Stuttgart, Germany, to Malmö, Sweden, on a single charge, arriving with 137 kilometers of remaining range. This real-world test, incorporating Formula One-derived engineering insights from Mercedes-AMG high-performance powertrains, underscored the technology's efficiency, thermal stability, and viability beyond laboratory conditions. The drive highlighted solid-state batteries' ability to maintain high performance across varied climates and road profiles, including highways and mixed urban segments. Mercedes-Benz has expanded testing fleets and continues partnerships to accelerate series production pathways, with prototypes evaluating overall vehicle dynamics, energy management, and longevity. While no firm consumer launch date has been announced for full integration, the company targets broader deployment later this decade, potentially in premium models where enhanced range and safety justify initial higher costs. Factorial cells promise superior energy density and reduced fire risk, aligning with Mercedes-Benz's vision for sustainable high-performance electric mobility. Other notable contributors include partnerships like BMW's collaboration with Samsung SDI and SolidPower for sulfide-based solid-state cells, with on-road testing in prototype i7 sedans demonstrating highway-capable performance. Stellantis explores semi-solid and full solid-state options through Factorial Energy investments, planning demonstration fleets around 2026. QuantumScape, backed by Volkswagen's PowerCo, has showcased high-throughput manufacturing processes and cell integrations in prototypes, including motorcycle applications, signaling progress towards scaled production. Samsung SDI advances oxide-based designs targeting 900 watt-hours per liter volumetric density, with sample deliveries to partners like Hyundai. These collective efforts illustrate a global ecosystem where Asian manufacturers lead in sulfide pathways, while Western and American players emphasize lithium metal and quasi-solid approaches. Industry observers note that while Chinese initiatives like Chery's Rhino S integration capture headlines for near-term deployments, legacy automakers such as Toyota, Honda, and Mercedes-Benz adopt more cautious, validation-heavy strategies to ensure long-term reliability and regulatory compliance. Small batch integration in limited production vehicles could begin as early as 2026 or 2027 for select models, serving as proof-of-concept platforms to gather extensive field data on cycle life, thermal management, and crash safety. Broader scaling toward the end of the decade will depend on overcoming remaining hurdles, including preventing cracking in solid electrolytes under mechanical stress, achieving consistent large-format cell yields, and driving down costs through automated manufacturing. Regulatory frameworks such as those emerging in China and Europe will guide safe commercialization, while investments in domestic supply chains reduce geopolitical risks. These ongoing advancements by major players signal growing confidence that solid-state batteries can transition from experimental prototypes to viable automotive solutions. With road tests yielding impressive results, pilot lines operational, and partnerships, solidifying the technology inches closer to transforming electric vehicle performance, potentially delivering ranges exceeding 600 miles, 10-minute charges, and enhance safety in production models within the next few years. As these companies refine their approaches, the collective momentum could redefine industry standards and accelerate the global shift towards sustainable transportation. If solid-state batteries scale successfully and achieve widespread adoption in the automotive sector, their transformative effects on the car industry could prove profound, addressing long-standing barriers that have constrained the full potential of electric vehicles while reshaping vehicle design, consumer behavior, ownership economics, and global mobility patterns. As of January 2026, with initial real-world deployments emerging in niche applications like electric motorcycles and planned passenger car integrations on the horizon, industry analysts and automakers increasingly view this technology as the catalyst capable of propelling electric vehicles toward mainstream dominance, comparable to or surpassing internal combustion engine vehicles. The most immediate and visible impact would manifest in the elimination of range anxiety, one of the primary psychological and practical hurdles slowing electric vehicle adoption worldwide. Current lithium-ion battery packs in mainstream electric vehicles typically deliver driving ranges of 300 to 500 miles under optimal conditions, with real-world figures often lower due to factors such as highway speeds, climate control usage, and cold weather performance. Solid-state batteries, leveraging higher energy densities frequently projected at 400 to 600 watt-hours per kilogram or more at the cell level, could double or triple effective range in comparably sized or even lighter battery packs. For instance, prototypes and early claims suggest ranges exceeding 600 miles, with some ambitious demonstrations targeting 1,000 miles or beyond on a single charge. This extended capability would make long-distance travel routine for electric vehicle owners, akin to refueling stops in gasoline cars, though with far greater intervals between charges. Families planning cross-country road trips, commercial fleets operating delivery vans or long-haul trucks, and urban commuters venturing into rural areas would face dramatically reduced planning requirements. Analysts project that such ranges could exceed those of many conventional gasoline vehicles, flipping the narrative from compromise to superiority and potentially converting skeptics who have cited insufficient range as their main deterrent to purchasing an electric vehicle. Closely tied to range improvements, ultra-fast charging times represent another game-changing benefit that could fundamentally alter refueling habits and infrastructure demands. Solid electrolytes enable higher current acceptance without the excessive heat buildup or dendrite risks associated with liquid systems, allowing prototypes to achieve 80% charges in 10 minutes or less, and in some bold assertions, full charges in as little as 5 minutes under ideal conditions. This speed approaches the convenience of filling a gasoline tank, which typically takes 3 to 5 minutes. For consumers, this means quick top-ups during coffee breaks, lunch stops, or errands rather than multi-hour home charging sessions or extended waits at public stations. The implications for daily usability are enormous. Road trips become seamless with brief pauses. Fleet operators gain higher vehicle utilization rates through minimized downtime, and overall convenience rivals or surpasses fossil fuel vehicles. Infrastructure adaptations would follow, with high-power chargers, potentially 1 megawatt or more, becoming prioritized at highways and urban hubs, though widespread deployment would require significant grid upgrades and investment. Early adopters in 2026, such as those receiving solid-state equipped electric motorcycles, already report charging adding substantial range per minute, hinting at how passenger cars could follow suit and normalize rapid replenishment as standard. Safety enhancements form a cornerstone advantage, potentially reducing one of the most publicized concerns surrounding electric vehicles. Traditional lithium-ion batteries carry risks of thermal runaway triggered by punctures, overcharging, or manufacturing defects, sometimes leading to intense fires difficult to extinguish. Solid-state designs eliminate flammable liquid electrolytes, relying instead on non-volatile solid materials that resist combustion and maintain stability even under abuse conditions like crashes or extreme temperatures. This inherent non-flammability could drastically lower fire incidents, easing insurance costs, regulatory scrutiny, and public perception issues. Enhanced thermal tolerance operating safely up to 150 degrees Celsius or more in prototypes reduces the need for heavy, complex cooling systems, freeing up space and weight for additional range or passenger comfort. In accidents, solid-state packs are less likely to propagate failure across cells, offering better crash resilience. For applications beyond passenger cars such as electric aviation, heavy-duty trucking, or urban delivery fleets where safety margins are critical, these improvements could accelerate electrification timelines by meeting stringent certification requirements more readily. Longevity and reduced ownership costs emerge as powerful economic drivers that could reshape total cost of ownership calculations. Conventional lithium-ion batteries typically endure 1,000 to 2,000 full charge-discharge cycles before capacity drops below 80%, often necessitating replacement after 8 to 10 years or 100,000 to 200,000 miles in vehicles. Solid-state batteries promise 5,000 to 10,000 cycles or more with minimal degradation, potentially allowing the battery to outlast the vehicle's usable life, 15 years or 300,000 miles in many cases, eliminating midlife replacement expenses that can reach $10,000 or higher today. Fewer replacements translate to lower long-term costs for consumers, fleets, and leasing companies, making electric vehicles more financially attractive over their life cycle. Maintenance savings compound from reduced cooling complexity and fewer thermal management failures. Environmentally, extended lifespans mean less frequent manufacturing of new batteries, curbing demand for mined materials and easing recycling pressures while supporting circular economy principles. The shift toward alternative materials in many solid-state designs could alleviate supply chain vulnerabilities and geopolitical dependencies plaguing the current lithium-ion ecosystem. Traditional batteries rely heavily on cobalt, nickel, and graphite sourced from concentrated regions with ethical and supply risks. Solid-state variants often incorporate more abundant elements, such as sulfur-based compounds, polymers, or oxides, potentially reducing reliance on rare earths and critical minerals subject to price volatility or export restrictions. This diversification strengthens energy security for importing nations, lowers raw material costs at scale, and mitigates ethical concerns around mining practices. For global automakers, more stable supply chains enable predictable production planning, faster scaling, and potentially lower end vehicle prices as material costs decline. Broader affordability and accessibility stand to benefit profoundly if manufacturing efficiencies materialize. Initial solid-state batteries carry higher costs due to specialized materials and processes, but economies of scale projected through gigawatt-hour facilities ramping in 2026 and beyond could drive prices toward parity or below lithium-ion levels by the early 2030s. Combined with extended lifespans and reduced ancillary systems, overall vehicle pricing becomes more competitive, especially in mass-market segments. Governments could accelerate incentives or mandates knowing the technology delivers superior emissions reductions, energy efficiency, and grid integration potential through vehicle-to-grid capabilities enabled by durable, fast-charging packs. In summary, successful scaling of solid-state batteries could trigger a dramatic acceleration in electric vehicle market share, potentially pushing penetration rates toward 50% or higher in key markets within a decade by removing core objections around range charging safety and cost. This shift would support aggressive global decarbonization targets, enhance energy independence through diversified materials, and enable seamless integration with renewable sources via bidirectional charging and long-duration storage synergies. While 2026 marks an exciting inflection point with early deployments validating performance claims, the industry's full transformation hinges on proven reliability at volume, aggressive cost reductions, expanded high-power charging networks, and supportive policies in the years ahead. Despite the wave of excitement surrounding solid-state battery announcements in early 2026, significant challenges and widespread skepticism persist within the industry, tempering enthusiasm with calls for caution and rigorous proof. As of January 2026, while startups and established players showcase impressive prototypes and deployment plans, the path to reliable, scalable commercialization remains fraught with technical, economic, and evidentiary hurdles that have delayed progress for years. A primary source of doubt centers on unverified performance claims from emerging companies, particularly those lacking independent third-party validation. For example, the Finnish startup Donut Labs unveiling at the Consumer Electronics Show of what it terms the world's first production-ready all-solid-state battery drew intense scrutiny. The company asserted an energy density of approximately 400 watt-hours per kilogram full charges in 5 minutes operation across extreme temperatures from -30 degrees Celsius to high heat, and an extraordinary lifespan of up to 100,000 charge-discharge cycles. These specifications, if accurate, would represent a monumental leap over conventional lithium-ion batteries. However, industry observers, including battery experts from major manufacturers and independent analysts, have highlighted the absence of detailed technical disclosures, peer-reviewed data, or external testing results to substantiate these figures. Reports from sources covering the event noted that demonstrations relied on physical mock-ups, such as three-dimensional printed enclosures, rather than fully transparent cell teardowns or live cycling evidence. Critics point out contradictions in the claimed parameters, such as combining ultra-high energy density with extreme fast charging rates and cold weather resilience without apparent trade-offs, leading some to question whether the technology truly functions as a battery or resembles advanced capacitor-like behavior in certain aspects. The company's decision to withhold specifics on chemistry confirmed to exclude lithium in some statements further fuels debate, as does the limited manufacturing experience of the small team behind it. Similar caution surrounds Chinese automaker Chery's announcement regarding its Rhino S solid-state battery, slated for integration into the XE Lifeng shooting brake model later in 2026. Chery claims a cell-level energy density of 600 watt-hours per kilogram using an oxide-based electrolyte, promising ranges up to 1,500 kilometers under the Chinese light-duty vehicle test cycle, even in sub-zero temperatures as low as -30 degrees Celsius. While impressive on paper and aligned with China's aggressive push in battery innovation, these assertions face skepticism due to the historical pattern of optimistic projections in the sector that often require years of refinement. Industry voices emphasize that achieving such density while maintaining safety, cycle life, and manufacturability remains unproven at scale, with calls for independent verification before accepting the figures as definitive. Historical delays in solid-state technology contribute heavily to the prevailing caution. For over a decade, solid-state batteries have been heralded as imminent breakthroughs, with major players like Toyota repeatedly adjusting timelines from earlier predictions to current targets around 2027 or 2028 for meaningful integration. Prototypes have shown promise in controlled settings, but real-world durability, particularly under mechanical stress, vibration, and repeated cycling, has proven elusive. One persistent technical obstacle is dendrite formation, where lithium ions deposit unevenly as needle-like structures that can penetrate the solid electrolyte, creating short circuits and safety risks. Interface issues between the solid electrolyte and electrodes also lead to high resistance, cracking, or delamination over time, degrading performance. These problems, long identified in laboratory research, have not been fully resolved in production-scale cells, leading experts to warn that claims of overcoming them without transparent evidence warrant skepticism. Mass production presents another formidable barrier, with manufacturing challenges driving up costs and limiting scalability. Solid-state batteries require specialized processes, such as dry room environments to prevent moisture contamination, precise layering of solid electrolytes, and handling of sensitive materials like lithium metal-anodes. Current estimates place production costs at 3 to 5 times higher than conventional lithium-ion batteries, often in the range of $400 to $800 per kilowatt-hour compared to around $115 per kilowatt-hour for mature lithium-ion packs. Exotic materials, including high-purity sulfides, oxides, or polymers, remain expensive and supply-constrained, while achieving uniform large-format cells without defects demands new equipment and techniques. Scaling from small pilot lines to gigawatt-hour facilities introduces yield issues, where even minor inconsistencies can render batches unusable. Industry roadmaps suggest that while small batch integration might occur in 2026 or 2027 for niche applications, broader automotive use requiring millions of consistent cells likely remains several years away, pending breakthroughs in automated, cost-effective fabrication. Regulatory and standardization efforts are emerging to address these gaps, but they too reflect the technology's nascent stage. In China, the world's largest electric vehicle market authorities released the first national draft standard for solid-state batteries in late 2025, focusing on terminology classification and basic testing criteria such as weight loss limits under vacuum drying to confirm solid electrolyte purity. This framework, part of a planned multi-part series covering performance, safety, and durability, aims to harmonize development and facilitate safe rollout. While a positive step toward guiding the industry, the draft underscores that no comprehensive automotive-specific standards existed previously, highlighting the need for rigorous protocols before widespread deployment. Similar efforts in Europe and elsewhere lag, creating uncertainty around global certification, crash testing, and long-term reliability requirements. Broader skepticism stems from the pattern of over-promising in the battery sector, where hype cycles have led to investor caution and delayed adoption. Past examples of bold claims followed by setbacks breed wariness, with analysts urging that real-world customer deliveries, such as those promised for Donut Lab-equipped Verge motorcycles in the first quarter of 2026, will serve as the ultimate test. If initial vehicles perform as advertised under diverse conditions, credibility could surge. Failures or underperformance would reinforce doubts. Meanwhile, established manufacturers adopt measured approaches, prioritizing extensive validation to avoid warranty risks and reputational damage. In essence, while 2026 brings tangible progress with prototypes and early deployments, the solid-state battery field grapples with unresolved technical barriers, high costs, manufacturing complexities, and a demand for independent proof that tempers revolutionary expectations. Overcoming these challenges through rigorous testing, cost reductions, and standardized frameworks will determine whether the technology delivers on its promise or joins the list of delayed innovations, shaping the pace of transformation in electric mobility for years to come. Should solid-state batteries deliver on their much-anticipated promise, the broader implications for transportation and energy systems could prove revolutionary, accelerating a fundamental shift away from internal combustion engines toward widespread electrification while supporting ambitious global goals for emissions reduction, energy security, and renewable energy integration, as of January 2026. With early real-world deployments such as Donut Labs' all-solid-state batteries powering production electric motorcycles from Verge Motorcycles and Chery's planned integration of its Rhino S solid-state battery into the Exceed Lifeng shooting brake model later this year. The technology stands at a pivotal inflection point. These initial steps, though limited in scope, provide concrete evidence that solid-state batteries can move beyond laboratory prototypes into customer hands, potentially catalyzing a cascade of changes across mobility sectors. The most dramatic near-term effect would likely appear in the acceleration of electric vehicle market share growth. Today's electric vehicles, constrained by lithium-ion batteries offering typical ranges of 300 to 500 miles and charging times measured in tens of minutes to hours, have achieved significant but uneven penetration, often hovering below 20% in many major markets. Solid-state batteries with demonstrated or claimed energy densities approaching 400 to 600 watt-hours per kilogram could enable ranges exceeding 600 miles routinely, with some projections and early assertions reaching 1,000 miles or more under optimized conditions. In the case of Chery's Exceed Lifeng, the company targets an extraordinary 1,500 kilometers under the Chinese light-duty vehicle test cycle, even when operating in sub-zero temperatures as low as minus 30 degrees Celsius. Such capabilities would dismantle range anxiety as a barrier, making electric vehicles practical for long-haul travel, commercial logistics, and regions with extreme climates. Combined with ultra-fast charging, potentially full charges in 5 to 10 minutes, this could push electric vehicle adoption rates dramatically higher, with analysts forecasting that premium and mass-market segments could see 5 to 10% penetration of solid-state-equipped models by the end of 2026. Scaling toward 50% or more in key markets by the early 2030s as costs decline and production ramps. This surge in electric vehicle uptake would deliver substantial environmental benefits by slashing transportation-related greenhouse gas emissions, which account for roughly 1/4 of global totals. Internal combustion engines, reliant on fossil fuels, emit carbon dioxide, nitrogen oxides, particulate matter, and other pollutants directly from tailpipes. Widespread replacement with electric vehicles powered by solid-state batteries, especially when charged from increasingly renewable-dominated grids, could cut sector emissions by tens of % in the coming decade. Solid-state designs often promise lower lifecycle carbon footprints through reduced material intensity, extended lifespans minimizing replacement needs, and compatibility with more sustainable sourcing. Studies indicate potential reductions of 24 to 39% in battery production emissions compared to conventional lithium-ion packs when optimized. As electric vehicle fleets grow, urban air quality would improve markedly, reducing respiratory illnesses and premature deaths linked to vehicle pollution, while contributing to international climate commitments under frameworks like the Paris Agreement. Energy security stands to gain enormously from the diversification of materials and reduced dependence on volatile supply chains. Current lithium-ion batteries heavily rely on cobalt, nickel, graphite, and lithium concentrated in a handful of countries, exposing manufacturers to price swings, export controls, and geopolitical tensions. Many solid-state approaches favor more abundant elements, such as sulfur, oxides, polymers, or even silver in emerging variants, potentially easing these vulnerabilities. For nations importing critical minerals, this shift could bolster strategic autonomy, stabilize costs, and mitigate risks from supply disruptions. In 2026, as early deployments validate performance with globally sourced materials, governments may accelerate policies favoring domestic or allied production, further decoupling transportation energy from fossil fuel dependencies and enhancing resilience against global shocks. A key enabler of broader systemic change lies in the seamless integration of solid-state batteries with renewable energy sources. Their superior cycle life, often exceeding 5,000 to 10,000 cycles with minimal degradation, makes them ideal for stationary energy storage applications, where batteries frequently cycle to balance intermittent solar and wind generation. Unlike shorter-lived lithium-ion systems limited to 4-hour durations, solid-state packs could support longer duration storage, storing excess daytime renewable output for evening peaks or multi-day lulls. This capability would smooth grid variability, reduce curtailment of renewables, and lower reliance on fossil fuel peaker plants, pushing renewable penetration higher. Vehicle-to-grid functionality already emerging with lithium-ion but enhanced by solid-state durability and fast bidirectional charging could turn millions of electric vehicles into distributed storage assets, providing grid services like frequency regulation and peak shaving, while rewarding owners through energy arbitrage or incentives. Beyond passenger cars, the technology's advantages: higher energy density for lighter packs, enhanced safety for high-risk environments, and rapid charging for operational efficiency, open doors to electrification in harder-to-abate sectors. Electric aviation, particularly short-haul regional flights and urban air mobility, could benefit from weight reductions and fire-resistant packs critical for certification. Heavy-duty trucking and shipping, where payload and downtime matter immensely, stand to gain from extended ranges and quick depot charging, cutting emissions from freight transport. Public transit, ride-hailing fleets, and delivery services could achieve higher utilization with minimal downtime, transforming urban mobility towards zero-emission norms. While 2026 marks this exciting milestone, with Verge Motorcycles delivering customer bikes equipped with Donut Labs solid-state cells in the first quarter and Chery advancing toward limited Exceed Lifeng production, the full transformation of the car industry and energy landscape will unfold gradually. Success depends on sustained reliability in diverse real-world conditions, aggressive cost reductions through scaled manufacturing, potentially approaching $100 per kilowatt-hour by the early 2030s, expanded high-power charging infrastructure capable of handling megawatt-level rates, and supportive policies including incentive standards and grid modernization. Regulatory bodies worldwide are developing frameworks for solid-state safety and performance, ensuring safe integration while fostering innovation. In the longer view, should these batteries prove scalable and dependable, they could redefine transportation as cleaner, more efficient, and more equitable, while bolstering energy systems resilient to climate challenges. The shift would not only decarbonize mobility, but also empower renewable dominance, diversify resource dependencies, and unlock new economic opportunities in manufacturing, recycling, and grid services. Early 2026 deployments represent the first tangible steps in what could become one of the most significant technological transitions of the century, with profound ramifications for economies, environments, and societies worldwide in the decades ahead.